Hi, welcome to my project demonstration video where today we're going to be going over the JK flip-flop. Here is the simplified circuit for it. We have J, K clock, and two outputs, Q and Q prime, which is just the inverse of Q. And the JK flip-flop is very similar to the SR flip-flop, where we have a clock, a set, and a reset. And it is gated where we have these AND gates. The other difference is that we have these outputs tied back into our AND gates here. To the truth table, one assumption of this truth table is that we're assuming that this truth table is under the account that our clock, which is a square wave, is only occurring during this rising edge. Everything else, all the way up until the next rising edge, does not matter. It is not taken into account. We're only looking at this rising edge, which is when this circuit will sample J and K. So when you first start up this circuit, you first give it power. The propagation delay of these circuits will determine whether Q will be 1 or 0 and Q prime will be 1 and 0. But they won't be the same value at the same time. They will always be the opposites of each other. Moving on to this truth table, like I said, we're only under the assumption that we are under the rising edge. Start up, propagation delay will determine which value has what. If you already have a value, if you set both J and K to 0, you will remain in the last state that you were in. When you set K to 1, you're essentially resetting it. You're setting it where Q is equal to 1, and then when you set J to 1 and K to 0, you are resetting it. So you're setting Q prime to 1 and Q to 0. The only difference, what distinguishes the JK flip-flop from the SR flip-flop is that in the SR flip-flop, S and R cannot be equal to 1. It's not a valid state. You can have it, but then Q and Q prime will be the same value, and that's not what an SR latch or flip-flop is supposed to do. So the JK flip-flop, when both are 1, that is a valid state, and you'll just remain in the previous state that you were in. So let's assume that Q was 1 and Q prime was 0. Okay, well, both are 1, so we have a 1 here and a 1 here. When the clock ticks, we'll have a 1 here and a 1 here. And since Q is 1 and we're feeding it back into this AND gate, we have a 1 here as well, which means we pass on a 1. And again, Q is 1 and we're feeding this back into this NOR gate. 1 NORed with 1 is going to give us a 0. This 0 is fed back in here. We have a 0 here. This Q prime, which is 0, is being fed into this AND gate. Therefore, we have a ANDed with a 0, therefore we pass on a 0. This is 1, and we remain in the same state as we were before. Now, let's assume the opposite. Let's say that Q was 0, and Q prime was 1. J is 1, K is 1. Clock is 1 on the rising edge, and in this case Q prime is 1, so we'll come up here, say this is a 1, we pass on a 1. Q is 0, this is a 0, Q is 0, we come down around, this is a 0, anything ANDed with a 0 is a 0, therefore we pass on a 1 with this NOR. This gets fed back up, a 1 NOR with a 1 is a 0, and we remain in the previous state that we're in. So that's pretty much a broken down JK flip-flop, and its difference between an SR flip-flop. J and K are valid. J and K equal to 1 are a valid input, and you feed back these outputs back into these AND gates. The VHDL code for the Vivato Zemix file is going to be in the video description below, and we're going and along it'll be included in the submission as well. So thank you for watching my video, and have a nice day.